discuss we will quickly revise the previous lecture, and then we will go on to unsupervised learning. We'll see in between the different kinds of learning methods which we typically encounter in machine learning. So in RL, we said that we started with the Flappy Bird example. We said our goal was to maximize the score. We said that there are a couple of actions that we could have taken, and the agent is the one who is playing in the environment. The environment is giving you the physics, it is giving you all the graphics, and the environment is beyond the rewards. It is also giving you some observations, which is some pixel level information, which you can then compress or you can store in something known as a state. We then looked at this main block diagram in reinforcement learning, where the agent performs an action at time t called a of t. The environment gives you some set of observations which you can then process to get the state, which is state at time t plus 1. You also get a reward, which the environment tells you whether the action was good or bad, and then you are in this loop. Is this happening for others in some other classroom also, or am I the only lucky one? We looked at the OpenAI gym environment, where we looked at mountain car and we saw a few other environments. We said that the goal is to maximize the discounted reward. So we put a discounting factor of gamma, where the reward at time t is called r small r t, and the total discounted reward is just a summation of rewards. We then created something known as a Q function, which stores the expected reward that you get by taking any particular action from any given state. So it's states, comma, action to the reward. So think of this as the table. We discussed this. You'll have a table where the different states are the rows, the actions are the columns, and the Q values are stored there. Given any particular state you are in, example S2, if you take the action 2, because it has the highest Q value, you're likely to get the best expected reward. So you'll choose that. We also discussed the fact that in many cases, the states, they are in a continuous space. So in the mountain car example, we had the velocity vector with the velocity, which was continuous, as well as the position, which was continuous. So we had to somewhat discretize it, because the Q table needs a discretized set of entries. And we looked at the Bellman equation, which is this recursive relationship between Q at state S, and then you take an action A, you get into state S dash. We then encoded this update rule, which seems similar to gradient descent update rule or perceptron update rule, and we then coded this up in a notebook, and we saw that we were able to learn, the agent was able to learn and was able to finish the game. So a next logical step would be to consider deep Q learning, but we will discuss that in a tutorial. There are a lot of nuances. It seems easy if you just write it out in theory, but to get it practically working, there are a lot of tricks which are needed. So we'll skip that. Instead, we will today discuss about the different kinds of learnings, and I'm again just referring to this very nice slide deck from Intro Deep Learning course at MIT. So we have been primarily looking at supervised learning thus far in the course. In the previous lecture, we looked at reinforcement, but primarily at supervised learning. The difference between these algorithms is that in supervised learning, let's say, so while it is kicking up, I will just speak out. What do you understand when you hear the term supervised learning? You don't need the slide, you can just speak out. What comes to mind when you hear the term supervised learning? Where is the supervision coming in from? So can you tell me any supervised learning algorithm? decision trees. When you fit a decision tree, what is the input that you give to the algorithm? What is the input that you give to the algorithm? Decision tree. Okay, firstly, what kinds of supervised problems have we seen? One is the regression problems. The other is the classification problem. So can you tell me, if I want to do a classification, what is the input that I give to the classification model? I give the input matrix X, which consists of different samples and their features, and I also give in the, some reason it's not working well. So the input matrix X and the corresponding label vector Y. Right, so those are the dimensions we've been thus far looking into. Matrix X, N samples. Okay, so as I mentioned, we are looking into the slide deck from Into Deep Learning MIT course, where we are now looking at the three classes of problems. Supervised learning, we're saying that the data which is given to us is pairs of the form X, where X is a feature vector and Y is correspondingly the label. In simple problems, Y is typically either a single scalar number or one of the classes in classification. So we are trying to learn this function which maps from X to Y. As an example, they've given an image. So if I have to say that this image is an apple, what kind of a problem am I solving? Classification, regression, reinforcement learning, classification. Okay. So can you start with an image and give me an example of a regression problem? Where would you use regression on an image like data? Image super resolution. Okay, so in image super resolution, what is the regression problem? Okay. Okay. So if you're trying to predict something which is also continuous, it's a regression problem. I was looking for something simpler. Super resolution is a harder problem and you can have a lot of variants of it. Okay, how many of you have used pulse oximeter, SpO2 monitors? How do they work? How does a pulse oximeter work? It's a 200 rupees device, so it can't be rocket science. What do you think? Right. So you could do those things with the phone also. So let's say if I had this phone with me and I record a video and I keep my, and if I keep my hand here, so I don't know if you can see or not, can you see something red? The entire screen is red. And can you see the pulsation? Can you see it pulsating? If you can see, then you have got Superman's eyes, because I can't see it. So the computer can see the pulsation. You would typically need a computer vision model to be able to see. I mean, at least from this far distance, you can't see it. So I can record a video like this, which is now a RGB video. So now given this RGB video, can you tell me how do you think of a regression problem where you're trying to estimate the oxygen saturation or the heart rate, let's say? Can you tell me that? Okay. Okay. Right. So it would also be good to understand the physics or the biology behind how this oxygen saturation or heart rate might be measured. What organ in the human body pumps the blood? The heart. The heart pumps the blood outwards. If the blood is going outwards, it will have some time to go from the heart to your fingertips. And your fingertips are at the end of the body, right? So that's why they are one of the better suited sites to measure your oxygen saturation or your heart rate, because that's a longer duration of travel. You could have also done at your at your feet, but this seems to be a natural fit. Right? So therefore, every time the blood comes to this part of the end of your fingers, depending on the amount of oxygen it has carries, the color will vary. And the intensity of the blood or the amount of the blood which is currently present, that will also be visible in the spectrum, in the RGB spectrum. Okay? So that is what you're trying to see when you're using some simple techniques like just fitting a camera, and sometimes you also put in the flash so that you get a better lighting conditions. So now can you tell me the regression problem? So because this is a supervised learning setup, you would also need a ground truth Y label. What would that Y label be in a regression-like problem? The actual oxygen saturation or the actual heart rate. Right? Typically, these are done in some aggregations. You don't do for an instantaneous, you don't do what is the heart rate at this 0.0001 millisecond. You don't typically do that, but let's forget that for a second. But essentially what you're trying to do is, given a video, which is a combination of correlated images, you have the ground truth heart rate and the ground truth oxygen saturation. How do you think those would be measured? Whenever we talk about supervised learning, you have to get the annotations via some ground truth process or some ground truthing process or some gold standard. How do you think we'll get the ground truth oxygen saturation or the ground truth heart rate? Sorry. There has to be some clinical grade device. So this 200 rupees device is something you can use at your own home. But that is clearly not the same device which they would be using in the ICU wards. In the ICU wards, they will have something which is hypersensitive, which is gold standard, which has been well calibrated. So something like that would be used as the ground truth. But this is also showing you the problems which we'll cover in one of the other classes of problems. So getting the ground truth, quality ground truth, is often very, very expensive. Right? Therefore, supervised learning is hard, because you're limited by the amount of high quality labeled data that you can get, and supervised learning cannot work without high quality labeled data. If the data is very noisy, you'll just learn a very noisy, erroneous function. Okay, so this was supervised learning. There has to be an explicit supervision, which is this Y vector which you give. In contrast, in today's class, we would be discussing unsupervised learning, where you're just given the data. You're not given the labels. You are just given, let's say, a bunch of images. You're trying to learn some underlying structure. We'll discuss a lot of variants of unsupervised learnings, but essentially what you want to say is you have to encode a notion of similarity. Given two fruits, I just want to tell whether they're similar or not. Given two digits, I just want to tell whether they are similar or not. I'm not telling what specific fruit this is or what digit this is. I'm just trying to tell you what specific digit, is this digit similar to some other digits. So I will come to this, but I can just show you for 1 second what I mean by this. So all of these digits, while I've given the labels, you don't actually assume that the labels are not there, but I've just put all these digits in a two-dimensional space. Now all I'm trying to say is that I'm trying to look for some structure. All the zeros in this two-dimensional space they occupy some portion of the space, of this two-dimensional space. Similarly, all the 4s occupy some portion, and all the 4s would be similar clustered together, all the zeros would be similar clustered together. 4 and 9 share some structure, right? You can just add one arrow to 4 and it becomes like 9. So therefore they are similar in this space. 9 and 7 are similar. You remove one of this curve and you'll get 7. Similarly, you're able to see the different structure which exists in these digits. So therefore, unsupervised learning, the important thing is there is no explicit supervision, no Y vector which is given. Reinforcement learning, we discussed in the previous lecture, where we are looking at the state action pairs. Given a particular state, what action do you take to maximize the expected reward? So in this Apple example, let's now, whenever you think about reinforcement learning, my main suggestion is to think of some environment or some gaming environment. Let's say you're playing a Super Mario-like game. There, if you see an apple, what is your reaction? Or when you play the snake game, you're given some fruits, right? What is your what is the reaction? What is what is the specific action that you take? You either eat the fruit or you don't eat the fruit. Right? You maybe maneuver around and you choose some different path where you choose not to eat the fruit. So therefore, in reinforcement learning, you are given these state action pairs. Is everyone clear on the distinctions between these three different classes of algorithms, classes of learning algorithms? Okay, so we will now go back to one of the questions which was asked in your previous quizzes. Okay, if you look at the first question, are we talking about supervised learning, or are we talking about unsupervised learning, or are we talking about reinforcement learning? Think for a second. If this was so trivial, I would not have asked. Okay, how many think we are dealing with supervised learning? How many think that there are multiple tasks in this question, one of which is definitely supervised learning? Okay, so I think you're getting there. The second task, where you are dealing with predicting the sentiment of a word or of a sentence, there you are given some explicit labels. You are given the labels of whether this is positive, negative, or neutral. So whenever you are given labels, that is a supervised learning task. But in the first question, the first part of the question, which is next character prediction, is that supervised or not supervised? How many think that is supervised? How many think it is not supervised? Okay, why do you think it is not supervised? Okay, but you do have the labels for the next character. So that is why this is a slightly tricky question if you just want to think from that perspective. So the first task is typically known as self-supervision, self-supervised learning, or what you sometimes also call as pre-training in the context of GPT-like systems. Right? So your overall goal is not to predict the next character. Your overall goal is to predict the sentiment of a word. For that overall goal, you have some labeled data, but you also have a lot of data which is lying for free. Like all of the Wikipedia text is available for free. But for all of the Wikipedia data, do you have for each word or each document, do you have the sentiment associated with it? No? But Wikipedia data is available for you. So the question is, for a lot of data which exists in the public, can you still use it in some way, which can then inform or which can make the downstream task or the task which you care about, can you reduce the amount of training required or can you make those better? Right? So let me repeat. Wikipedia text or some similar text like data is available for free. All of us have web pages. We have a lot of text that is available for free, but we don't have any supervision there. I do not have the sentiment associated with the different documents or the different words. If I have to do that, what do I need to do? If I have to label the sentiment associated with different words on Wikipedia, what do I need to do? I need to have a human annotator who will sit and who will then tell whether this word is positive, negative, neutral. But that we have just discussed is very expensive. At the same time, the Wikipedia text is available to me for free, essentially for free. So the question is that, can I use the Wikipedia text, which is available for free, use it in some way which can then inform my usage for the more important downstream task? The way I do this is by something known as self-supervision. You take, let's say, a sentence. I don't know the sentiment of the sentence, but from this sentence, I know the next character. Right? So I have the X value, which is the X matrix, which is a sentence. I manipulate it in such a way that I pose it as a supervision task, supervised learning task, which the task is to predict the next character. Right? I don't have the labels for the downstream task, which is my sentiment task, but I do have the labels for the next character. So therefore, I'm using the input itself, which is not explicitly supervised, but I'm providing some notion of self-supervision. Right? The label is coming from the task itself, from the pre-training task itself, or you have some way of generating some labels. So next character prediction is one such self-supervision task. What could be some other self-supervision tasks for text-like data? One is next character prediction. What could be some other similar one? Fill in the blanks. One is you predict just one timestamp into the ahead, one character ahead, but you could also have some characters to the left, some characters to the right, and you're trying to predict some character in between. That is like the fill in the blanks or masking like problem. Important thing is, again, you do have the labels available to you. You're just manipulating the input in order to get the correct labels. Right? So therefore, this kind of a paradigm is becoming very popular these days. You have a self-supervised pre-training task initially. In this case, the task to predict the next character. This helps you to learn embeddings. The embeddings or the relationships between the different characters. You start off with that set of embeddings, and then you focus on the downstream task. And you have solved this question yourself in the quiz. Instead, if you were to focus only on the downstream task, do you have very limited amount of data available? Because labeled data is hard to get. So therefore, maybe you just have 100 words in your labeled data set. Whereas Wikipedia is, let's say, billions of words or billions of pairs of words, right? So therefore, you're able to learn a very good embedding space through the first task, which you can then fine tune for the downstream task. Therefore, the downstream task is clearly supervised learning. The upstream task or the pre-training task is self-supervised learning. So downstream tasks, so we typically, let's say so you have something known as pre-training, which you expect, so these embeddings which you have created, you expect to use them for varieties of tasks. One such task is to predict the sentiment of the word. What could be some other thing which you want to do with text-like data? One is sentiment. One could be, let's say, predict the polarity of a word. One is sentiment, one is polarity. What could be some other thing? Another could be given an email, you want to classify it as spam or not spam. Right? Again, which is email is a bunch of text, you want to classify it as spam or not spam. So we have now looked at three different tasks. We'll call them as downstream tasks, which are our application tasks. And our pre-training, which was common, or of a self-supervised task, which was common, can be fed as the initialization of the embedding for each of these tasks. Right? So previously what people were doing was to create very specific models for each of the tasks. They'll have a model for spam classification, they will have a model for polarity detection classification, and they'll have a specific model for detecting the sentiment. You have three different models. But now what we're saying is that none of these models have access to a lot of data. Therefore, they are not going to be very well generalizable. Instead, we use a pre-training task. In the self-supervised way, which is learned on a lot of data. We learn some embeddings through them. We just fine-tune those embeddings for the individual downstream tasks. Does that make sense? Any question on that? You can call this transfer, or you can just call this, you have a embedding at the top, and you're just fine-tuning it. I mean, there are a lot of nuances to these specific terminologies being used. But I just wanted to show the important thing that even without knowing the fact that there is something known as self-supervised learning, you people solved it in your assignment. If I was just expose you to study self-supervised learning, you might have got overwhelmed. But you were able to solve, many of you were able to solve these questions in your quiz. So this is one way to think about self-supervised learning in the case of text. In the case of images, it's probably a little easier to think. So let's say I am, let me start off with a simple task. So let's say you're given some images. Now again, images on the internet are available for free. Labeling those images is expensive to you. So I will give you a self-supervised task, a task, pre-training task. I start with an image. I myself rotate it by 90 degree, 180 degree, 270 degree. And my task is to be able to predict the amount of rotation that an image has gone through. Now, do I have the labels for each of the rotations which I have done? Yes, because I have done it myself. Did I need any explicit supervision? No, because I'm not labeling anything like whether it's a cat or a dog, etc. So that's the hope. By using some simple pre-training tasks in the self-supervised way, self-supervised because starting from the input itself, you do some simple manipulation of the input and you're able to get the generated label, and then you're trying to do a classification problem or classification like problem. Through this, you learn the embeddings or you learn the encoding, and that you can then use for your downstream task, which could be, let's say, classification. Is self-supervised learning making sense? How it is different from supervised learning? The main idea is that the supervision or the labels are coming from some pre-specified task which you can yourself give. Fill in the blanks, next character prediction, or rotation, predicting the rotation, or image in painting. All of these are some self-supervised tasks. The next category is known as semi-supervised learning. One such example of semi-supervised learning is something known as active learning. So thus far we've been discussing about the fact that getting the labels is very hard. One way to reduce the amount of labels required is via self-supervised learning. The other is via active learning or similar methods. So here the idea is that you start off with some small labeled data set. You learn a model on that. And you have this, again, infinite, assuming close to infinite amount of data which is unlabeled, right, which does not have a Y label corresponding to it. So there is a set of methods which then look at this unlabeled data and tell the human annotator which of these images or which of these inputs would be most useful to add to your training data set. Right? So all the inputs will not be equally important. Maybe some other input is, some specific input is more useful to me. And that is what this specific class of algorithm does. We'll not go into the details, but this is just to show that you will always have these variations where you have a lot of unlabeled data always available to you. In supervised learning, you will label the data. Unsupervised learning, you'll just look at the unlabeled data, try to recover some structure from it. In reinforcement learning, you have some goals in mind, play like games like setup. In self-supervised learning, you will use the unlabeled data and create labels from it in some pre-training task. In active learning, you look at both labeled data and unlabeled data. And your goal is to select from the unlabeled data those samples which will make your model the best, improve the best, improve the quickest. Okay, any questions on these classes of algorithms? So having discussed that, we will be now discussing unsupervised learning, where we just given the output data without the input, or we are not given the labels explicitly, and we are trying to recover some structure, learn some structure from the data. So we will be looking at a few categories of unsupervised learning methods also. The first one is known as clustering. So term clustering comes in from when you're trying to identify clusters of stars. It's some structure which exists in the stars. So in this case, if you have weight and height, you end up clustering these set of population into two categories of people. So why do you think clustering like activities are useful, where you're separating out the data into some different clusters into different groups? Why do you think that might be useful? I don't really have the labels for these. I don't really know whether these are early risers, whether these are healthy people, unhealthy people. I don't know them directly, but still grouping them gives me some value. Why do you think that? That is the case. So typically with mobile phone operators, sometimes they need to do some targeted advertisements. Targeted advertisements, as in if they want to give you some custom plans, they will have different custom plans for people who are less than 20 compared to people who are, let's say, between 50 and 60. So they need to do the segmentation of the market and need to figure out what is the right product fit for the each individual category. So these are the kinds of applications for clustering. You're subgrouping your data so that you can have some different interventions or different targeted advertisements for each of the group. Similarly here for different weight sites, maybe you want to target them differently and give them some different exercise regimes. So here we have divided the data into two clusters, where you need to understand how each point is likely to belong to each of the cluster. Another interesting application is, this is showing me the energy consumption for some homes. I don't know whether this is UK or the US. For a lot of homes, and I've plotted this with alpha equal to very small value so that I can see all of these homes. Can you observe some patterns? This is the energy consumption, and the x-axis is the hour of the day. Just by looking at these curves, can you tell me something? Okay. So depending on the hour of the day, there is some different energy consumption patterns. That is the obvious thing. What can you tell me between hour 1 and hour 7? Most homes have what? Low energy consumption. Does it make sense? Most people are sleeping, so the energy consumption would be low. During between 6 and 8, almost all of the homes see a spike. Why is that? People wake up, they start preparing food, they start preparing for school, office, etc. Now, there is two sets of energy consumption patterns that we can see. Right? One of them seems to have high energy consumption, the other seems to have low energy consumption between 8 and 6 p.m. What could this tell you? There are some homes where people stay, and there are some homes where people go to offices, etc. Okay. And then there are, during the night time, 7 p.m. or so, I think everyone just starts preparing for the dinners, and then maybe they turn on the air conditioning during this night, something like that. Almost all of the homes do. So therefore, we can see some 2 or 3 different load curve patterns. Now, if I have to do any specific interventions for them, I can look at their individual profiles. I can understand that these people should be given some different kind of actions. For example, these people, the red cluster, they are typically very low energy consuming customers. Any effort that I spend on them is probably not going to be very useful. Whereas the green ones, they consistently consume a lot of energy. Maybe if I want to sell energy efficient fridges, I should go to them. Or energy efficient air conditioners, I should go to them. Whereas the blue ones, I can perhaps tell them to improve their thermostat settings so that their energy consumption of the air conditioner is slightly reduced. Something like that. So I can make some targeted interventions by doing some clustering. There are other categories of unsupervised learning algorithms. The other one is known as dimensionality reduction. We have already studied dimensionality reduction in one of the assignments where we were given some high dimensional activity data. We wanted to just show them in some 2-dimensional space. We did this also when we were trying to learn the embeddings. So we want to reduce the dimensionality of the data by projecting the data to a low-dimensional subspace. One benefit of doing this is we make the problem more interpretable. We are able to visualize our data. What could be some other benefit of reducing the dimensionality? The memory would reduce. Okay, what else? We remove unwanted features. Thereby we avoid what curse? The curse of dimensionality also. There could also be very highly correlated features, we get rid of them. For example, this is 2D data, but I can actually project it to just one-dimensional data. Most of the information is just lying along this one particular line. So there are algorithms like PCA, TSNE, UMAP, some of which we have already used. We'll come to them later. So this is also showing a dimensionality reduction. A 28 by 28 pixel, 784 dimensional vector is shown in this 2D space, I think using UMAP or TSNE. And you can very nicely visually see the structure which exists. I was discussing this just a few minutes back. Like there are some commonalities you can see. All the 4s are similar, all the 9s are similar, and then 4 and 9 are also similar. We have already discussed the matrix completion problem. We have also seen the matrix completion problem in the context of image in painting. So therefore, these also we can put in the category of unsupervised algorithms. And there are some other interesting variants. We're trying to discover the graph structure, like a social network graph structure or the social network as in Facebook-like networks, or the dynamics of, in general, of the society. You're trying to discover via some graph structure. So we'll look into clustering now, which is the first unsupervised class of algorithms, where we're trying to find some groups or subgroups in the data set. But in order to do that, we would need some notion of what is a group or how we define similarity. Previously also we have discussed the notion of similarity via some Euclidean distances in the k nearest neighbor lectures. We directly go on to the algorithm, the k-means clustering algorithm. Before I show the algorithm, I would just show you the demo of this. So I have this data. I'm trying to now divide this into subgroups of data. Not a very good example, and you'll also see why this is one of the examples where k-means algorithms don't work very well. There is something known as, So I will say that I want to do a I want two classes in my clustering, or I want two clusters. So I start with, randomly I put 2 points, throw 2 points, and I say that these are perhaps my cluster centroids. I don't know the clusters, I don't know the groupings of point, but I just randomly put 2 points in the space. And the next step is that all the points in the dataset which are closer to the red point, they will be assigned the red cluster. All the points which are closer in this dataset, closer to the blue point, will be assigned the blue cluster. Once I do that, I will then look at all the points which were assigned to the red cluster and find the centroid of that. I will look at all the points which are assigned the blue cluster, and I will find the centroid of them and update the centroids. So therefore, the red centroid should perhaps come somewhere over here, and the blue centroid should come somewhere over here. Now, next, when this happens, I will look at all the, so you can see here that after the centroids have been updated, it seems like there was few red points which would now perhaps are closer to the blue centroid. So now I look at all the points in my data set, figure out which of them are closer to the red centroid, and figure out which are closer to the blue centroid, and assign those. So if I do the reassignment, you'll see that these points have now become closer to the blue centroid and their labels have changed. Once I do that, I again need to look at all the red points now and figure out the centroid. Look at all the blue points, figure out the centroid, and update the centroids. I keep doing this, and after a while you will see that I have more or less stabilized. It will very minutely update, but more or less it's stabilized. So if it is stabilized, it means that my training procedure or my k-means procedure has converged. Here I started with 2 centroids. I will now perhaps start with 3 and let me put them in their eyes. Oh, sorry, this is just random. Okay. So I have now put 3 centroids. So I'm learning 3 clusters and I do the same procedure now. So, and now let me go back and add 4 clusters. Okay, which of these is the best clustering? With clusters 2, with 3 clusters or 4 clusters, and why? In general, do you observe that as I increase the number of clusters, the variation within a cluster is reducing? As I increase the number of clusters, the variation within a cluster is reducing. Let's go back and see. If I just have 2 clusters, right? So now for the red cluster, what is the variance along the x dimension? It is this space, right? A lot of points are there. What is the variance or what is the range of points along the y-axis? It's about a semicircle, right? So this is showing that there is a lot of variance in my clustering for small number of clusters. If I increase to 4 clusters, okay. What is the range for my green cluster in the x dimension? If it's much smaller, what is the range in my for my green cluster in the y dimension? Again, it is smaller. So therefore, do you always get a better clustering using this notion of variance amongst a cluster as you increase the number of clusters? Right? You'd expect to see that. If I go to the extreme for n data set for n points in my data set, if I increase the number of cluster centroids to n, will I get a clustering with each point being a cluster? Right? So there is no variance. It's a perfect clustering in that sense, but it's a poor clustering in the other sense because you're trying to recover some structure in the data. And that structure you want to do by some groupings. Right? So therefore you will have to figure out a way to optimally define the number of clusters. So we come back to the algorithm mathematically if you look at it. We have some endpoints in some d-dimensional space. We say that Ci is the set of points in the ith cluster. We know that the unions of all the points in the different clusters will be all the points, and no 2 clusters will have any common points. So therefore, this is also known as hard clustering. There are some soft clustering methods like expectation maximization, where a point can be distributed across multiple clusters with some probability. But in this case, each point belongs to a unique cluster. And I'm showing now a data set where I have set k equal to 5 means clustering. So I'm also now showing the k equal to 6, 5, 4, 3 clusterings for this data set. And we somehow need to define what is a good clustering, what is a better clustering. One intuition which we will use in this lecture is that within the cluster the variation is small, which is what I was mentioning as the ranges of the points which are assigned to a cluster. Within the cluster the variation should be small. Otherwise, what you're trying to say is that I have a lot of variance in the subgroup which I have identified, which does not make sense. A subgroup has to be some coherent quantity, some coherent structure with a lot of similarity. So therefore, the within cluster variation has to be small. Therefore, we come up with the objective that across the k clusters which we are trying to produce, if we sum up the within cluster variation of the individual cluster Ci refers to the cluster containing some set of points. If I sum that up, I'm trying to minimize that. Now, the question to you is, what mathematical formula might you want to write to for within cluster variation? How do you mathematically define some quantity like this? I gave some intuition as to look at the ranges. That can be one definition of within cluster variation. What could be some other definition of within the cluster variation? Yeah. So essentially, you can say something like within cluster variation for a cluster Ci is 1 over the number of points in the cluster Ci and the distance between all the pairs of points. The distance between all the pair of points, we can write it as xa minus xb, which is summed over all pairs of a's and b's in the data set. Right? So this would give you how close different points are within the cluster. And the algorithm was what we saw in the demo a few minutes back. You randomly assign a cluster center. We started with putting some centroids initially. Then for each cluster, we compute the centroid mean of all the points in Ci over d dimension. So there are two variants of this, which are essentially the same. You could either assign each point a cluster, or you could first start with identifying a set of centroids and then pick up the points which are closest to the centroid. Right? So both of them would give you the same answer. It's just that where do you start off with. And then you just iterate till convergence. We had seen the demo. There is another nice demonstration that you can take. If I just do 2 clusters and if I iterate over the algorithm, you'll see that how the colors will keep changing and the distinction between the 2 clusters will also keep changing. Now here, interestingly, when the method which I had used to generate the data had 200 points and 5 clusters. So naturally this won't be represented very well using just 2 clusters because the within cluster variation seems to be very large. If I had indeed kept it to be 5, do you think I'll do a very good job? Not necessarily, because this is also not a perfect method in the sense that you may not recover the original clusters, because this is also a greedy method in that way. So if we reinitialize to 5 clusters, you iterate over these. Here it seems to be doing a very good job, but it may not necessarily discover the exact structure with which we started. The specifics of why we can rewrite this expression 1 over the number of points in Ci and the distance between all the points, which is looking at all the pairwise points, and how that relates to the centroid, that I leave up to you as a exercise, as a homework exercise. So this particular expression that you're seeing, this does not involve the centroid. Right? This is looking at all the pairs of points, but somehow you have to be able to get the centroid in this picture. And there are some nice properties which exist, which you can use, where you'll be able to show that if you are able to get the centroid for the ith cluster in a particular way, which is just the average of all the points in that space, and then you can use that xi instead of all the pairs of points. You should be able to see that there is you can write both these methods equivalently. I'll not show the details. I'd want you to work this out on your own, so that you can see why the centroid is being used in this algorithm. So by this time I typically get in via cross validation. Can you use cross validation to figure out the optimal number of clusters? Why or why not? What did we observe? As we increase the number of clusters, the within cluster variation always decreased. Therefore, we cannot use any cross validation like methods over here. Whatever data that you use, if you have more number of clusters, your objective will always be lower. Right? So, therefore, we end up using some heuristic like methods, like elbow method, k-means. Let's use this example. So let's say this y-axis that you're watching is observing is your within cluster variation or your objective, and your x-axis is the values of k. As you increase the number of clusters, the within cluster variation summed over the different clusters will always reduce, but beyond a point you observe that the reduction is very slow. The reduction is almost close to zero, which is also known as point of diminishing returns. So therefore, at beyond that point, there is no point in dividing the data into further subgroups because you're not extracting a lot of information. And in terms of structure, this looks similar to the elbow joint. Right? Therefore, this is known as the elbow joint method for determining the optimal number of k. So beyond a point where the reduction in the objective is below a certain threshold, you stop over there and you decide that as the optimal number of clusters. So it's heuristic. You could have come up with any other heuristic. Any question in this? In contrast to k-means learning, there is another method which is known as hierarchical clustering. And hierarchical clustering would give you hierarchy of clustering. So we don't need to pre-specify a k. You just do the clustering along all the possible hierarchies, and then you decide based on it the visual structure. I'll directly go over the algorithm, and then you should be able to see how it is different from k-means clustering. We'll initially start with all the points in a single cluster. Right? So therefore, you can think of this as equivalent to k equal to 1 means clustering. 1 means clustering. All of these points are now in one cluster. Which 2 points do you think are the closest? Which pair of points do you think is the closest in this data set? 2 and 3. To identify the 2 closest points, you merge them into a single cluster. So you merge 2 and 3 into a new cluster, and perhaps you call that cluster as 2, 3. It contains these 2 points. So therefore, if you notice, the y-axis is, you could think of this as the distance between the pairs of points or the pairs of clusters. 2 and 3, they joined at this distance of, let's say, 5 units. Right? So therefore, at y equal to 5, you draw this dendrogram-like structure and you merge them into a single cluster now, which is some 2, 3. Next, you look at this 2, 3, you would replace with these 2 points, you would replace with another point, which is, let's say, the midpoint of these. And that midpoint of these would now perhaps also be close to 1 or 4. And if you notice that 2, 3, when you have combined, that is very close to 4. Right? So that has some distance. That gets joined at this particular distance. And so then you will also join this and create a new structure like this. And on the other side, then you'll see 7 and 8, they are close to each other. So you'll combine them into a supercluster, into a cluster. And then when you have combined them, that becomes closer to 10, so on and so forth. So now in this structure, if I have to identify any k-means equivalent like clustering, similar to that, I can always just make a vertical cut. If I make a vertical cut at y equal to 1, how many clusters do I have? If I make a cut at y equal to 1, what equivalent to k-means clustering have I done? 10 clusters, right? Each point is an individual cluster. There is no aggregation. If I do look at my y equal to, let's say, 60, I make a vertical cut. How many clusters am I getting in the data set? 1 cluster. If I make a cut at y equal to 35, how many clusters do I see? 2 clusters. One which is 5, 1, 4, 2, 3, 5, 1, 4, 2, 3, 1 cluster, and the other cluster is 8, 9, 7, 6, 10. Now, similarly, if you keep making more cuts, you'll be able to have more number of equivalent to k-means clustering. Now, there are few variations in this, where you look at the distances when you're joining or you're looking at the linkages. You could look at the minimum distance between the points in 2 clusters, or you could look at the distances between the centroids of the 2 clusters, or you could look at the maximum distance between any 2 points in 2 clusters. Right? So we were looking at these distances, right? When 2 and 3 are combined, I'm joining them with 4. Now I could look at 3 kinds of distances. I could look at the maximum distance. So if I look at the maximum distance, what is that distance? Between 2 and 4 or between 3 and 4? What distance should I be looking at? 2 and 4? Because 2 is farther to 4 compared to 3. So if I look at the maximum distance, it's between 2 and 4. If I am using the single linkage, single clustering, I look at the minimum intercluster similarity. So then I would look at between 3 and 4. Or I could look at the centroid one, in which case I would be computing the centroid of 2 and 3, and then look at the distances to 4. So you could use any of these 3 variants to decide how to do the hierarchical clustering. Okay, any further questions? If not, we'll end today slightly early. In the next class, we will either have a tutorial on some k-nearest neighbor algorithms, k-nearest neighbor approximate algorithms, which we are also discussing which we are also asking you to solve in the assignment. Or we'll look at the next topic, which is either dimensionality reduction or naive Bayes.